Okay, so all of you are there. Okay, good afternoon, guys. We'll start. I'm sorry for being a little late. I had a meeting to attend, so the class will go till 7:40. Okay, because we're starting by approximately exactly 6:10. So the class will get completed at 7:40. Okay, right. So today it is solid state and solution. Is it? Yes. No. Is it solid state and solutions or some other chapter?
Solid state and surface chemistry, sir.
Solid state and surface chemistry. Okay, cool.
Yes.
Right. Cool. Thank you. Fine. So first, maybe we'll do solid state. We'll do some questions, and then we'll move on. Okay. Right. So I think the semiconductor part is omitted for you, isn't it? The last part, the doping, N-type semiconductor, P-type semiconductors,
Sure.
those things are omitted. Okay, fine, cool. Right. Right. So you have to know certain things for you to do the problems, right? The first one would be what are the different types of unit cells, right? And the different parameters regarding different unit cells, and that would be say, for example, right? Okay, so we have basically a simple cubic, and you have okay, we'll see one by one. Simple cubic, and we have body centered cubic and face centered cubic. These three are the one which are there in your syllabus. Other than this, we have edge centered, vertex centered, so many, so on and so forth. But those things are not there in your syllabus. There's something wrong with the angle. Okay, suppose it's fine. Cool. Right. So if I take simple cubic, right? So we have to understand where and all are the lattice points, right? Fine. So okay, can someone tell me what exactly do you mean by a lattice point? What is a lattice point? Can anybody tell me what is a lattice point?
Intersection of two lattices.
No. So in lattice point, what do you see? What is there in a lattice point?
Unit cell, sir.
Unit cell has lattice points. In lattice points, what are there? What is there on the lattice, or what are lattice points composed of? Right. So guys, these things you have to know, right? See, please understand. Right. Say, assume that I have a solid with me, right? So the chapter starts with what are the different types of solids. You have something called as crystalline solids. You have something called as amorphous solids, right? So you have to understand the basic difference between these two, right? So crystalline solids are going to have proper structure, right? And amorphous solids are not going to have any proper structure. The arrangement of atoms are going to be in a random manner, but in a crystalline solid, it is in a specified manner, right? Okay, right. And then the other different properties like your crystalline solids are going to show anisotropy, right? What do you mean by anisotropy and isotropy? Crystalline solids are going to show anisotropy, and amorphous solids are going to show isotropy. What do you mean by anisotropy and isotropy? Come on, I know you. I know that you know the answer to this question. Come on, tell me.
Sir, physical quantities when measured over different locations are having different values, something like anisotropy.
Exactly. Correct. So if you see, guys, say I take an crystalline solid, right? Say you can put any arrangement, but it should be a proper arrangement. You can, I'm putting it like this. Any kind of shape you can bring here. I'm just putting a normal thing here, right? Say assume that I'm going to measure any physical quantity. For example, say resistance, conductivity, refractive index, any density, anything for that matter, any physical quantity I'm going to measure, right? So if assume, see, if I measure it along this direction, for example, right, and say I measure it along this directions, for example, right, there I'm just taking two different directions, right? So you see the path which I'm taking here are actually going to cover the number of atoms covered in these two directions are different, is it not? Say you see here in this case, if I'm going to take this direction, right, the number of atoms are actually pretty less, is it not? These are the atoms present or the molecules present. The path which I'm taking are not actually coinciding with any of the atoms or molecules, at least approximately, right? But if I'm going to take this one, right, I see that actually some of the atoms are actually coinciding with the path which I'm taking, right? So obviously what is going to happen, so I have difference in the occupancy of atoms on the different directions. So obviously along these two different directions, if you're going to measure any physical quantity, it is going to give me different values, right? So this property of measuring physical property along different directions and that yielding different values, that is what is called as your anisotropy, right? Okay, so obviously isotropy means obviously the opposite of this, right? So whenever I'm going to measure along any two different directions, I'm going to get the same value of that particular physical quantity, right? So you can understand how is it. Say it's going to be a random arrangement of atoms in case of amorphous solids. So you take this direction, any direction you take, approximately that it is going to have the same value, because the path taken will have the same number of atoms or molecules which are going to get encountered, right? So this is going to show isotropy, right? And we have something called as long range order, short range order. Your amorphous solids are going to have long range order. Your crystalline solids are going to have short range order. What do you mean by long range order and short range order? Anybody want to comment? What is long range order and short range order? How many of you are there? I think enough number of people are there, right? Only 3 of you are there. Oh, no, 4. Oh, okay. Then the strength keeps on decreasing day by day. Cool. Right. So what do you mean by long range order and short range order, people? Okay. So I suppose fine. So it's pretty easy, right? So what do you mean by order? Proper arrangement, right? So you see, in this particular case, say if I take this particular space, if I'm going to take, there will be some number of atoms, right? Say now if I'm going to take some 2 Armstrong units away, 2 Armstrong units are very small unit, but still when we go for solid molecules, that's what we speak. So if I'm going to take another this thing, I might not have the same arrangement. I can have some other kind of arrangement. Like assume that in the center of the solid, right, in the surface of the solid, I'm going to have different arrangements, right? That is why we call it a short range order. That particular orderly arrangement of atoms is not going to be seen throughout the solid, right? Only short ranges you are going to see proper arrangement of atoms. Okay, now if I'm going to take an amorphous solid, you can easily understand, right? Like wherever you go, it's completely randomly oriented, right? Randomly arranged. So there definitely wherever you see approximately, you can say that I'm going to have same arrangement, even though it's random. Everywhere it is random. That's the point, right? So that is why it is going to show long range order. Right? Okay. Now we are not going to study about amorphous solid in our solid state chapter. We are going to study only about crystalline solids. Okay. Right. Fine. So when I go for crystalline solids, right? When I go for crystalline solids, First thing what you have to understand is what do you mean by a space lattice, or a lattice for that matter, right? When I say space lattice, or I simply call it as lattice, what do you mean by this is pretty simple, right? Say I take crystalline solid, okay, right? Say assume that I have a crystalline solid here. Now what I'm going to do is I am going to divide this solid into, with the help of vertical and horizontal lines, right? Say vertical, I mean, these are the horizontal lines, these are the vertical lines, okay? So assume that this is the entire solid, okay, right? So I'm going to divide them into equal parts with the help of your vertical lines and horizontal lines, okay? So what is going to happen? Now you will see, now how should you put the vertical lines and horizontal lines is the next question, right? So what you have to understand is when I put the horizontal and vertical lines, obviously you will see that there are going to be points where the horizontal and the vertical line meets, okay, right? Anyways, so before we move on to that, you have to understand that this entire thing is what is called as space lattice, right? So the entire solid divided into small units with the help of vertical and horizontal lines, that arrangement, how it looks, is what is called as your space lattice, or generally called as lattice structure. Basically, lattice means structure. Okay, right. So now how we have to construct the vertical and horizontal lines should be in such a way that the meeting points, all the meeting points I have, right? If I'm going to put myself, or if I'm going to make you smaller, and I'm going to make you sit on these lattice points, or these are what are called as lattice points, okay, right? So how should be the lattice point is what I'm talking about. Lattice point means the intersection of the horizontal and vertical lines, okay? So I'm going to make you smaller, and I'm going to make you sit onto these lattice points, okay? So what you should observe is that irrespective of whichever point I'm going to put you in, right, irrespective of whichever point I'm going to put you in, the environment you are going to see around you is going to be same environment. I don't know how do you, have you like any of you seen Interstellar movie? Have you seen Interstellar? Did you see? No? Yes? Okay, so
No,
Niveda
sir.
says yes. Okay, fine. So if you have seen that movie, right, there'll be a scene where that guy will actually get trapped into a quantum loop. We don't have to go into the details, right? So that guy will trapped into a space, okay, and you will see that this exact kind of arrangement will be there, horizontal and vertical lines, okay. So what will happen is, like if he just moves one step, or say 2-3 steps, whatever he does, wherever he moves inside that particular loop, right, he will see that whatever around him he sees, it's going to be exactly same, right? So that is what I'm trying to explain you. If I'm going to make you smaller, and if I'm going to make you sit in these lattice points, right, irrespective of which lattice point I'm going to put you in, right, like for the first point or second point or third point, whichever point, if you see around you, you are not going to see anything different from the first point to the second point. The environment around you is going to be exactly same. Okay, right, fine. So we understood what is a space lattice. What do you mean by a lattice point? Okay, and the next thing comes. Now what I'm going to do is I am going to take the smallest possible unit from this lattice. Okay, smallest possible unit. Say this is the smallest possible unit I am going to take. Okay, now this smallest possible unit, it should be in such a way that if I take it out and replicate it in all the 3 possible directions, x, y, z directions, okay, I'm going to take it out and I'm going to replicate it, reproduce it in all the 3 directions, you must be able to produce your entire space lattice. Okay, again I repeat, you are going to take the smallest possible unit, and how should you take it? You should take it in such a way that this particular unit, when replicates in all the 3 directions, should produce the entire space lattice or the lattice, right? Now that smallest unit is what is called as your unit cell, right? That smallest unit is what is called as your unit cell. Now you're seeing this in 2D, but eventually this is going to be in 3D, because I'll not be able to show you. right? So based on that, like basically it is going to be basically a shape where I'm going to have 8 vertexes. Okay, so you can speak like this. Anything else? Okay, fine. Right. Okay. So now, obviously, if you for every crystalline solid, it is not going to be a cube. Definitely not. Right. So now, what kind of shape you are going to attain is going to based on 6 parameters. Okay, this is my x, y, and z directions. Okay, so assume this is x, this is y, this is z. You can put anywhere, anything you want, unless like this thing that they are mutually perpendicular. Okay, right. So there are going to be 6 parameters, right? The 6 parameters are actually going to be this length A, this length B, and this length C, right? And the angle between them, alpha, beta, and gamma, right? So based on these parameters, right, how they are related to each other, right, accordingly you are going to get different shapes. And it's very simple for us to understand that if I have A is equal to B is equal to C, alpha equal to beta equal to gamma equal to 90°, obviously you are going to get a cube. Is it not? Because I know in cube all the sides are same and all the angles are going to be 90 degrees, right? So like this, one of the possibility, if you have this particular condition, then you are going to get a cube. And you have other type of unit cells also. What are the unit cells? You have orthorhombic, rhombic, tetrahedral, so monoclinic, so on and so forth. Now, for all the things, these things only will vary. Maybe A is equal to B, but not equal to C, or say alpha, beta is equal, all are equal, but not equal to 90°. So many things you'll get. So like that, you will be getting 7 crystal systems, right? 7 crystal systems, right? So 7 crystal systems are basically going to be based upon all the 6 parameters, 3 sides and 3 angles. Okay, right, fine. So now again in our syllabus, we have only cube. We have just the simple crystal system to be simple cube. Simple cube. I'll just call it as cubic crystal system. Okay, right. Now, now we understood what do you mean by unit cell, right? What do you mean by crystal system? All this stuff. Okay. Now, in this cube itself, in this cubical crystal system itself, based on where the points are, I showed you points in such a way that this is how the points are, but it need not be always like this. I can have some other kind of arrangement, right? So based on where the lattice points are, and first thing foremost, what do you mean by a lattice point? Lattice point I explained you with this, but what is there in a lattice point is the question now, right? So in a lattice point, it can be atom, one atom can be there, or it can be a fraction of atom, say 1/3 of an atom, 1/2 of an atom, or it can be a group of atoms, say 2 atoms, 3 atoms, 4 atoms, something like that, or it can be a molecule, or it can be an ion, like say Na plus Cl minus, right? So what you have to understand is basically a lattice point is consisting of an atom or a group of atom, molecule or ion or a fraction of atom. All these things are possible in a lattice point. Okay. Now, based on I understood that simple cubic is my crystal system, right? Now, based on where the lattice points are present, first thing you will get is what is your simple cubic. Right. So we'll try to understand what you mean by simple cubic. Then you have body centered cubic. Then you have face centered cubic, edge centered cubic. All these stuffs are there. So we'll see what is there. What are these things? Okay. Right. Fine. So any questions till now? Okay. I suppose there are no questions. Hope I didn't confuse you. Right. Everything is understood. Okay, fine. So now when I say simple cubic, it's pretty simple for us to understand. It's all about where the lattice points are. Now what you have to understand is in all the corners, I am going to have a lattice point. As simple as that. Okay, I have 8 corners and all these 8 corners are going to have 1, 1, 1 lattice point. Okay, that is the structure you have to understand. Right. Now, what are the other things you have to know for a unit cell? Then what you have to understand is what is the number of atoms per unit cell. right? Number of atoms per unit cell. How many are there in a simple cubic? How many atoms per unit cell? How many atoms per unit cell in a simple cubic?
One.
One is the answer. It's pretty simple how you remember it, right? See, please understand there are 8 lattice points. Okay, and I told you all lattice points will consist of atoms. Very easy. Okay, right. Now, what you have to understand is that I told you this is the smallest unit. This is the smallest unit of the entire lattice. I told you this, if you're going to replicate in all the 3 possible directions, you are going to get the entire lattice, right? Okay, so what I have to understand is this each and every point where I have lattice point I have in the unit cell is not only for this unit cell. Please understand that from a particular point, right, I can draw 8 lines. I can draw 8 lines. That means a particular lattice point will be shared by 8 other cubes. Basically, 8 cubes can come out of the single lattice point. It's pretty easy to understand. North, east, west, south, northeast, northwest, southeast, southwest. 8. Right? Okay. So from a single vertex, you will be able to generate 8 more cubes like this. Okay. So what I understand, these lattice points are not going to be only for these unit cell. It is actually divided, or it is this particular lattice point is divided among 8 unit cells. Okay. So I have 8 lattice points, and the contribution of one lattice point to this unit cell is only 1 by 8, because one lattice point is divided among 8 other unit cells. Correct? And that's why we get 1 atom per unit cell. Okay, 1 atom per unit cell. This we have to understand. Okay, fine. Now, next, what you have to understand is, so when you go for packing efficiency, right, you know what you're going to do in packing efficiency. You are going to put some spheres, so on and so forth. You do not have to worry about the derivation part. Okay, all you have to understand is the relationship between the edge length A. Obviously, these are the edge length A. And if I'm going to put some spheres, how the radius of the sphere and this edge length are related. And I'm going to give you the direct answer. A is equal to 2R, and this works good for a simple cubic unit cell. Okay, A is equal to 2R. This you have to remember it. Okay, then if they ask you what is the packing efficiency and they ask you to find it, you just put this, and then what you have to understand is it is basically the packing efficiency. Right, packing efficiency will be volume of the sphere divided by volume of the cube, entire cube. Right, so volume of the cube I know is A cube. I know what is the volume of the sphere. Volume of the sphere is 4 by 3 pi r cube, and this will be A cube. Now you have to put the values, either A, you substitute A for R or R for A, and then you calculate it. Right? Now, what you have to understand is only 1 atom per unit cell. Anyways, don't have to worry about it. So you will approximately getting 56% as the packing efficiency for simple cubic. Right? Fine. So what you have to understand, what and all you have to remember? Number of atoms per unit cell. What is the relationship between A and R? And what is the packing efficiency? These things, if you understand, any problem can be solved easily. Okay. So this is for a simple cubic. Right. Okay. Next thing, what we understand is a body-centered cubic, BCC. Right. In body-centered cubic, again, what you have to understand is where are the lattice points. I know that again all 8 corners are there. Right. Now, from the name itself, you can understand at the center of the unit cell. At the center of the unit cell, I am going to have a lattice point. Okay. Right. So now, obviously, all the other 8 lattice points, exactly this thing stays as such, because again, each corner lattice point will be divided among 8 other unit cells, 8 other cubes, right? But what is there in the center is exclusively for this unit cell. Is it not? How will I put cube inside a cube? If I put that, if I'm going to replicate it it is not going to fetch me the entire lattice, right? So what I understand is this lattice point is exclusively only for this particular unit cell, right? So now if I go for number of atoms per unit cell, 8 into 8 is equal to 1. That is for the corners, and entirely 1 for the body center, right? So totally you have 2 atoms per unit cell for body center cube, right? Okay, next. What is the relationship between A and R? Can you tell me what is the relationship between A and R for body centered cubic?
4R is equal to A root 3.
Okay, so basically R is equal to root 3 by 4A. What you said is obviously correct, right? So R is equal to root 3 by 4 into A. This again you have to understand. Packing efficiency will be little more. You don't have to remember the exact value of packing efficiency, but what you have to understand is the packing efficiency is very minimum for the simple cubic, little intermediate for BCC, and the maximum packing efficiency is for FCC. Right. Okay. So that is about BCC. Right. Now when I go for FCC, that is face-centered cubic. Right. Again, face-centered cubic is again going to have all the lattice points here like this. Okay. And then you are going to have 6 faces. Please understand, you can take your room, for example, right? Your room is again a cube, right? So you understand, behind this I have a wall, behind your behind this phone I have a wall. So that is one face, this is one face, this is another face, this is another face, down and up, 6 faces, right? Now from the name itself you can understand it is face centered, so you have 6 faces, is it not? Now what I have to understand is what is the is this particular lattice point in the face, say this face has one, this face, this face, this face, like I'm not able to show you properly, but please understand, in the center of each face I have a lattice point, right? Now please understand, if you're going to take, say, assume that this is my wall of the room, this board is the wall of the room. Now you can easily understand that this wall can be common to this room as well as the next room, is it not? Right, this wall will be common to this room as well as to the next room, the other side, right? So what I understand is each phase is actually divided among 2 cubes or 2 unit cells, right? Okay, so what I understand is 8 into 8 is 8 into 1 by 8 is 1. Other than that, I have 6 faces, right? And these 6 faces, the contribution of each face center lattice point is 1 by 2. Just now we discussed this can be divided among 2 rooms, right? So obviously I have 3 for this, and totally 4 atoms per unit cell for FCC, right? Okay, then again, what is the relationship between A and R for this? Can someone tell me?
Four R is equal to A root 3.
Okay, fine. So you have R is equal to A by 2 root 2. Can I write it like this? Okay, right? R is equal to A divided by 2 root 2. You have to remember this. Okay, again, the packing efficiency is maximum for FCC, right? Next thing is about the voids, right? Like you don't have to worry about, see, you have only 2 types, you have actually so many types of voids, but what is predominant are only 2 types, tetrahedral voids and octahedral voids, right? Okay, so how will I understand how many voids or how many tetrahedral voids, how many octahedral voids per unit cell will be there, right? That we'll try to understand. Okay, right? So please understand that the atoms or molecules, it is not necessary that the atoms or molecules should be there only in the lattice point, right? It can be there in octahedral voids also, or it can be there in the tetrahedral voids also. We'll solve some problems like that. Okay, right, fine. So for that, it's a very simple explanation I'll give you. The logic you don't have to, if you try to understand, it's okay, but I'm not going to give you the most, we're not going to get into the logic of how is this coming, because it's pretty, I'll take a lot of time for me to explain mathematically how is it, right? So if I have n atoms per unit cell, right? If I have n atoms per unit cell, okay, right, then I will have n number of octahedral voids, right, and 2n number of tetrahedral voids. This simple stuff you need to understand. Okay, if I have n atoms per unit cell, right, then I'll have n number of octahedral voids and 2n number of tetrahedral voids, right? For example, if I take FCC, right, FCC has how many atoms per unit cell? FCC has how many atoms per unit cell? Just now we saw, what is it? Number of atoms per unit cell for FCC is?
Four.
Right, 4. So you have 4 atoms per unit cell for FCC. That means it will have 4 octahedral voids and 8 tetrahedral voids. That is what you need to understand. Okay, 4 octahedral, mean if the number of atoms per unit cell is 4, that means I'll have 4 octahedral voids and 8 tetrahedral voids. As simple as that. Okay, so why am I telling you all this is because they will give you some information. They ask you to find the formula of the compound. Okay, so for that only I'm telling you all this. Fine, this is one thing, and there is one more formula and questions can come from that. That is the density of the unit cell, D. Hope you remember the formula. It is Zm divided by Na into a cube, where D is the density, Z is the number of atoms per unit cell, M is the molecular mass, Na is the Avogadro number, and A is the edge length. And they will not give you A directly. They will say that R will be given, and they'll give you what is the type of the unit cell. You have to remember what is the relationship between A and R, and that has to be substituted here. Okay, fine. D is equal to Zm divided by Na into A cube. You have to know what are these parameters. Z is number of atoms per unit cell, M is molecular mass, Na is Avogadro number, that is 6.023 10 to the power 23, and A is the edge length of the unit cell. Okay, right. Other than that, I have to go for the defects: frontal defect, Skotsky defect, mental deficiency defect, mental excess defects, right? All these things we'll see some questions. Okay, so I think now we will look into some problems. So a lot of problems are coming from this direct formula substitution only. You don't have to worry about it. I'm just looking for a problem where you have to find the formula. Again, it's all about density. Direct. I don't want to solve that problem. It's not easily the formula substitutions. I am just looking for. Oh, maybe you don't have problems like that. No, you don't have problems like that. Okay, fine. But anyways, if I have to give you a problem, right? Fine, I'll give you. Right. So there's a compound. Okay, there is a compound which is made of A and B, some element A and B. Okay. I tell that A and B forms a compound, it forms a crystal in a cubic closest packed structure. Right, I'm telling you that A and B is going to form a crystal, right? It is going to be a cubic closest packed structure in which A occupies all the lattice points, right? And B occupies, or let me make the question a little easier. A occupies all the vertex lattice points, right? And B occupies the face centers. Okay, and I'm asking you, what is the formula of the compound? Can you tell me what will be the formula of the compound? So actually, I should if I gave you directly face centers here, right? See, when I say cubic closest packed structure, the first thing which should come to your mind is FCC, because I know the packing efficiency for FCC only is maximum. Okay, right? Fine. So now you see that A is occupying the vertex lattice point, that is the corner lattice points, and B is occupying all the face centers. What is the formula of this particular compound? If I ask you, what will be your answer? So if A occupies all the corner lattice
AB4?
points, AB4, no, it's, do it properly. Okay, so A is occupying all the corner lattice points. That means how many atoms per unit cell will be there for A? I know the contribution is 1/8 and I have 8 corners, so I'll have only one A. Is it not? Right? Now, when I go to B, they say that it is occupying the face centers, and I know I have 6 faces. The contribution of each face is 1/2. So basically, how many I have? 3 B's I have. So what is the formula? AB3. This will be the formula. Yes, everybody understood. How is it AB3? A is occupying only the corner lattice point, so 8 into 1/8, only 1. And B is occupying all the face centers. So I can easily understand that there are 6 spaces. Contribution is 1/2. So they'll have 3 B's. So these are only there per unit cell. You can easily understand 1A and 3B. So the formula will be AB3. Yes, everybody understood? Yes, no? Okay, fine. I suppose if you didn't understand, please ask me. I still don't know how many of you are there. Okay.
Yes, sir.
Okay, some amount of people are there. Okay, so I got one answer there and understood. Good. Fine. So this kind of problems can also be asked. Other than that, the problems will be asked from density. Definitely density, one question will come. Easily formula substitution, 2 or 3 marks. You just substitute and do the calculation properly. You are going to get the answer. Okay. Now, other than that, you will obviously get the questions from different types of defects. Okay, right. Fine. So when we go for defects, okay, maybe I'll ask you directly questions. Okay, what type of stoichiometric defect is shown by AGBR and AGI? AGBR shows what defect? AGI shows what defect? AGBR shows what defect? AgI shows what defect?
AgBr shows Frankel as well as Schottky,
Okay.
and Ag, I think so, shows only Schottky.
Okay, your AgBr is correct, right? So AgBr shows both Frenkel as well as Schottky defect. AgI shows only Frenkel defect. Okay, guys, are you thorough with what do you mean by these defects? Obviously, I have to know the examples. Examples are very important, which will show what to say, which will show Schottky defect, which will show Frenkel defect. All these things you have to understand. Do you know what is Schottky and Frenkel defect? Everybody is thorough with it, or you want me to explain?
Can you explain it once, sir?
Okay, fine. I'll explain. Right, just give me a moment. 1 second. Okay. Okay, where is my marker?
Sir,
Yeah.
if suppose we say that cation or anion is found in all the lattice points, then what do you take as a number of atoms?
They cannot tell like that. If cations and anions are there in all the lattice points, they have to specify like say cation is there in which kind of lattice points and anions are there in which kind of lattice points. They have to specify it, or else you'll not be able to give it.
It's like cation occupies 2/3 of octahedral void, and anion B is in all lattice points.
Good. Okay.
So
Did they say which unit cell? Did they say?
No, they didn't give the unit cell.
Okay. So if they didn't give you any unit cell, by default it is FCC. Please remember this. Okay. Right. If they didn't give you any unit cell, that means it is FCC by default. Okay. So then now only I told you what is about the number of octahedral voids and number of tetrahedral voids. Okay. So what I understand is you told me the anion B, or whatever be the anion, it is occupying all the lattice points. That means I know the total number of atoms per unit cell in FCC is 4. That means basically I have 4 anions. I can directly say this. Okay. Now what you told is 2/3 of what? 2/3 of
Octahedral voids.
2/3 of octahedral voids. Okay. So I know that 2/3 of octahedral voids. So I'll have basically 2/3. Now total number of octahedral voids I told you will be equal to the number of atoms per unit cell. Correct, right? So if it's for the cation A is occupying 2/3 of the octahedral voids. So the number of octahedral voids is 4. Because in FCC or whatever be the unit cell, the number of atoms per unit cell is equal to the number of octahedral voids. Okay, so what will be the answer? It will basically be 8/3. Now that's it. You just have to take it. So A is to B is basically 8/3 is to 4. Now obviously I cannot have for fractions here. So multiply this by 3 and multiply this by 3. So this will become 8 is to 12. Right? 8 is to 12. How can I write it? 4 is to 3. So what will be the formula? A4B3 will be the answer. Understood? Very easy. Number of octahedral voids is similar, same as the number of atoms per unit cell. So they said that all the lattice points are occupied by FCC. I mean, by the anion. So the number of atoms is 4. Number of anions is 4. Right? And the number of octahedral voids is as similar, same as the number of atoms per unit cell. But they're telling that the cations are occupying only 2/3 of this, not all of them. Right? So 2/3 of 4 will become 8/3. So if I take the ratio of A is to B, you have 8/3 of A, and for B it is 4. I don't want to have any fraction, so I multiply both by things. So it'll become 8:12. So it'll become 4:3. Formula will be A4B. Is it okay?
Yes, sir.
Okay, so in a binary, okay, that's a question. One second, I'm coming to the question. In a binary compound, atoms of A form a HCP lattice. So whenever you see HCP structure, it is FCC. Okay, remember that. And those of M occupy 2/3 of tetrahedral voids of the HCP structure. What is the formula of the binary compound? Very, very similar to this problem. Now, instead of octahedral voids, they have asked you tetrahedral voids. That's the only difference. So what you have to do, same thing for A. This would have been A, FCC, 4 atoms, done. Now, if it was tetrahedral voids, what you have to put is 8 here, because I told you, if the number of octahedral voids and the number of atoms per unit cell are same, and the number of tetrahedral voids is double the number of octahedral voids, right? So if I have 4 octahedral voids, I will have 8 tetrahedral voids, right? Done. So it will be 2 into 8/3. So this will become 16/3. So all you have to do is 6. Okay, for A it is 16/3. This is 4. So I multiply this by 3, this by 3. So this will become 16:12. So this will. Did I do something wrong last time?
It was supposed to be A2B3. You wrote A4B3. 8:12.
Okay. I understand. So now it's actually 4:3. I'm sorry. There was a small calculus mistake previous time. Please bear with it. So now this will be the formula. Okay, there was a very small calculus mistake. I'm just wondering how is it the same formula. Yeah, just a small mistake last time. This time it's correct. Okay, the formula will be A4B3. Okay, so I think whomever asked that question, I think it was Anirudh, if I'm not wrong. Yeah, Aditya. Okay, Aditya, I hope you understood. Right? Okay, good. Right, so we'll see these defects. So we'll see what happens. Any other questions you have? You want to ask? Okay, so I suppose there are no questions, but we'll just see what are these defects, and then we'll quickly go for surface chemistry. Right. Right. So please understand, guys, a perfect lattice should look like this, right? Say I have A plus, B minus, A plus, D minus, D minus, A plus, D minus, A plus. Again, the same thing here. I'm going to have A plus, D minus, A plus, D minus. So what you have to understand is alternate cation and anion is what you need to have. This is a perfect lattice, no defects at all. Okay, right. So the defect is going to come, right? Defect is going to come if I'm going to do something with the arrangement here. If something is putting ulta pulta, something is not there in its position, if it's somewhere else, or if it is even not there in the entire lattice at all. So those kind of stuffs are what is going to create problems for me. Okay, right. So what is going to happen is, first thing, if I look at Schottky defect, first we'll see frontal. Oh yeah, fine. Okay, whatever it is, Schottky defect. Right. So what is going to happen is there will be loss of one anion and one cation. As simple as that. Okay, there will be loss of one cation and one anion. Okay. Now please understand, people. If you're going to remove any cation or any anion for that matter, the charge balance should still be there. The whole lattice as a whole should be neutral. Okay, so what I'm trying to tell you is, in a Schottky defect, there will be loss of one cation and one anion. As simple as that. Okay, say for example, I take this out, right? That becomes a defect. And again, the lattice cannot stay like this because it is not neutral yet. So somewhere I have to remove a B minus. See, I have A minus removed, I have a B minus removed. So done. Okay, right? This is what is called as your Schottky defect in very simple words. Okay, so obviously what I understand is some amount of A and B are lost, right? So obviously the molecular mass or the mass of the compound or a mass of the lattice is reducing. whenever the mass is reducing, you will see that the density will be decreasing whenever you have Schottky defect. Okay, whenever you have Schottky defect, Frontal defect, we'll see Frontal defect. Anyways, so you will see that there'll always be decrease in density of the lattice whenever you have Schottky defect. Okay, right? So what kind of these things will be able to show? KCl, AGBR. These are the very common examples. KCl and AGBR are the ones which will show Schottky defect. Okay, right. Fine. Now, when I go for frontal defect, we'll see what happens. Right. So I hope it's understood. One cation and one anion is lost. As simple as that. Very simple. But you should not take like consecutively these two should not be lost. Say A somewhere you take, B somewhere else you take. I took it from here, you can take it from here, or you can take it from here, anywhere you can take. But not consecutively. Okay. So that is about Schottky defect. Fine. Now, when I go for frontal defect, okay, so in frontal defect, again, I'll write all the stuff. This is the perfect crystal. Okay, now this is my perfect crystal with no defect. Okay, so in frontal defect, what happens is, right, one of the A minus, or say one of the cations, right, one of the cations is not going to be at its position at all. Okay, one of the cation is not going to be at its position. So where is it going to be? It is not going to go out of the lattice as the previous case. In previous case, what happened? 1A minus, 1A plus was completely lost. It was out of the lattice. Right? Here, the A plus is not going to be there in its position. It is going to be somewhere else in the lattice. That's the only difference here. Okay. Say, for example, I remove this A minus. Right, and I put it somewhere, not in the lattice point, but somewhere in the interstitial sites. Interstitial site. Interstitial site is an empty space inside the lattice. So there, the A plus can be present. Okay, right? This is what is called as your frontal. Right, so obviously anions will not be able to do this. Generally anions are bigger and cations are smaller. Okay, so only cations will be able to do this. Okay, right, fine. Now, what is the density problem? Do you think will I have any density problem here? Will I have any increase or decrease in density?
No, sir.
No, because nothing is lost. It is just not there in its original position. It is, but it is still there, but somewhere else. Right, so here no density change. Right, here I'll have no density change. And which kind of compounds will be able to give is when I have AgCl will be able to give, AgI will be able to give, any zinc salt, zinc chloride, zinc iodide, all these can also give your frontal defect. Okay, now these are what are called as stoichiometric defects, right? These are what are called as stoichiometric defects. What do you mean by stoichiometric defects? The stoichiometry is not affected. Now you saw it last time also, 1A was lost and 1B was lost. So the ratio still remains the same. Is it not? Say for example, if it was 4:4, when it is perfect lattice, when Schottky defect happened, it will become say 3:3. But still the overall ratio is what? 1:1. Hope you're trying to understand what I'm trying to say, right? So if I had 4:4, assuming, right? Say 1A was lost and 1B was lost. So now what will happen? It will become 3:3. But what is the overall ratio again? Overall ratio is still 1:1, right? So here also you see the number of A's and number of B's are still same. The stoichiometric amounts or the ratios of A and B are not changing, right? So that is why these are what are called as stoichiometric defects. There is no change in stoichiometry. Okay, now when I go for, do you have non-stoichiometric defects also in your syllabus? Metal excess defects, metal deficiency defects, do you have?
Yes, sir.
Okay, fine. So we'll look into it then. Right, fine. So I hope there are no questions here. All you have to understand is what is frontal, what is Schottky, density changes, and what are the examples for frontal and Schottky. Okay, right, fine. Now, when I go for non-stoichiometric defects, I'll not write fully, right? When I go for non-stoichiometric defects, because of this defects, there is going to be change in the stoichiometry. Okay, there is going to be change in stoichiometry. Okay, right. So now these can be of two types, right? I can have metal excess defects, or I can have metal deficiency defects. Now, from the name itself, you can understand. Okay, fine. So now, when I go for metal excess defects, okay. One second. Okay, now metal excess, fine. So now I'll just write the lattice again. So I'll just write 2 rows for a simplicity. Okay, so this is a perfect lattice, right? Now we are talking about metal excess. Now please understand, metal excess can be visualized in 2 ways. One, actually there is a metal excess. I have, say, the number of cations are greater than the number of anions. Or other way of looking at it is the number of anions is less. I hope you understand. Either I add one extra cation to create a metal excess, or I remove an anion to create a metal excess. Either way, the metal will still be in excess. Is it not? Again, I repeat. Either you add extra cation, that is one way, or you remove an existing anion from the lattice. So either way, you are going to create a metal excess defect. And both ways, we'll see what is going to happen. Okay, right. Say first case, I remove an anion. Okay, say assume that I don't have a B minus. Right? Now, please understand, still, if you remove a B minus, okay, stoichiometry is gone. Stoichiometry is gone. Is it not? It's not again anyways going to be 1:1 anymore. Right? But still, the overall lattice should be neutral. The charge neutrality should be there. Right? So what is going to happen? What is going to happen is, instead of an anion, I just have an electron occupying that position. All I need is a negative charge, isn't it? So that negative charge in this case is going to be an electron. Okay, so what I'm creating a metal excess by removing an anion from the lattice. Okay, by removal of the anion, I still have to maintain charge neutrality, right? So the charge neutrality is maintained by adding an electron. We don't have to add electron. You know, obviously A plus would have formed by losing electron. So that electron from somewhere can come and occupy here. And this position occupied by electron is what is called as?
F center.
Absolutely. These are what are called as F centers. Very easy, right? Here in this case, the metal excess is created by removing an anion. Okay, cool. Now, what is the next step? Now, or what is the other way of creating a metal excess defect? Now, by actually adding extra cation. Okay, so again, we'll go back. So F centers are there. Okay, cool. So now, again, here what was there? Here I had a B minus. Oh, fine. This is the perfect lattice, right? Now I add an extra cation. That is actually going to create metal excess. Is it not? Now you see that all the lattice points are already occupied, right? All the lattice points are already occupied. So if I have to add a cation, I can add a cation only to the interstitial site. That means the voids which are there. Say somewhere here I add a. This is not a lattice point. It is somewhere. This is what happens. I have a sodium chloride crystal. I pass sodium vapors to it. Obviously, say sodium plus ion will not be able to occupy the lattice point, but sodium plus ion will be able to occupy the interstitial voids or interstitial points, right? So again, what you have again, same goes with your KCl. KCl crystal pass potassium vapors over it. Same thing is going to happen. This is going to impart some color. Now, why is it going to impart some color is the question. right? So we know that sodium chloride crystals are white in color, but the moment you're going to pass sodium vapors, it is going to become, I think, yellow in color, if I'm not right, if I'm not wrong. Okay, so fine. So you added A plus. That A plus has gone and occupied an interstitial site. So again, you have to maintain charge neutrality, right? Now charge neutrality again will be, I just have to add a negative charge, and again I cannot add a B minus. If I add a B minus, there's no point in creating a metal excess again, isn't it? So what I have to do is add an electron, right? Now again, you see last time the electron was occupying a lattice point and that became an F center. In this case, no lattice point is available, right? So the electron will try to again occupy an interstitial site. As simple as that. Okay. Now the color which you're talking about, I have a sodium chloride crystal. When I pass sodium vapors over it, it is going to become yellow, is because of this electron. Right? Why? Because this electron is now free, right? So now it can go to higher level, it can go to lower level. Say it jumps from one level to another level, some amount of radiation will be liberated out, right? And that radiation, if it falls in the visible region, right, that electromagnetic radiation is going to come out. If it falls in the visible region, you are going to see some color, right? Okay. So you added an extra cation, and it is not going to occupy the lattice points. It is going to occupy the interstitial sites, right? And again, for charge neutrality, you have to add an electron, and that is also going to occupy the interstitial sites. And this can go higher in energy or lower in energy if you supply something. And if the energy released, if it falls under visible spectrum, then I'm going to see some color, right? Okay, so that is about metal excess defects. Okay, fine. Now when I go for metal deficiency, again, two ways of looking at it. How metal deficiency? By adding extra anion, one pathway. By adding extra anion, so the anion becomes excess, the cation becomes deficient. Or the other way, exactly, removing an cation from the system. Removing an cation from the system, right? Okay, so we'll see what is going to happen. Okay, this is the perfect crystal, right? Say I assume that first case, I remove a cation out, right? I remove a cation. Now I have created metal deficiency. Is it not? Because I've removed a cation. Now again, guys, please understand, you have to understand that there still be charge neutrality which has to be maintained. Okay, so what is going to happen is one of the A plus, say this one, instead of being an A1 plus, it is going to become A2 plus. Very simple, isn't it? I removed a cation, so I created metal deficiency. I still have to maintain charge neutrality. So what is going to happen? One of the A plus will become A2 plus. Loss of one positive charge. Now by becoming 2 plus, addition of one positive charge, so the electron neutrality is still maintained. So what I understand is which kind of metals will be able to give this. Obviously, any metal is capable of showing multiple oxidation states like manganese, chromium, all these can show +2, +3, +4, +5. Right, so anything which can show multiple oxidation states will be able to show this kind of effect. Okay, right. Now the last one, metal deficiency by adding extra anion, right? Adding extra anion, A plus, again I write properly, this is a perfect crystal, right? Now if I add an extra anion, where it will go? Again, it has to go to the lattice point. So I have to put a B minus here. So again, I created excess anion. Thereby, I created metal deficiency. Okay, right. But this is not going to happen. Why? Can you tell me? Whatever I told you now, by adding extra anion and that extra anion occupying interstitial site is not going to happen in reality. We are not going to see it happen in reality. Why? A normal guess, any logical guess. You need not be right. Nobody wants to guess? Okay, so maybe I'll answer then. So I know cations are smaller, so they will be able to occupy interstitial sites, but generally anions are a little bigger. Okay, so this B minus will not be able to occupy the interstitial sites because it is bigger in size, right? So that is why we don't see this happening in reality. But the other one which you saw, removal of an A plus and the other A plus becoming A2 plus, that is possible in reality. This is not possible in reality. Okay, right? So that is about all the type of defects we see. Frenkel, Skotsky, metal excess, 2 types, metal deficiency, 2 types, but only one is going to happen in reality. Okay, any questions? Everybody understood all the defects? Please give me a yes. Please give me, everybody put in the chat box if you understood, yes or no, please. Okay, 1 S, 2, 3.
Yes, sir.
4. Okay, fine. I hope everybody understood. Yes, fine, good, good. If everybody understood, even I'm good, right? Wonderful, wonderful. So that is about the chapter. Okay, from now on, any questions coming from this chapter, you will be able to answer it. Okay, fine, wonderful, right? So next part will go for surface chemistry. Okay, now in surface chemistry, first thing what we have is about adsorption, right? Okay, so we have to understand what is adsorption, what are the different types of adsorption, physical adsorption, chemical adsorption, right? And then you have to understand this adsorption isotherms. Okay, these are all there in adsorption. And then you again have catalysis and you have colloids. Is colloids a separate chapter or it comes under surface
Catalysis
chemistry?
is removed from the syllabus, sir.
Catalysis is removed from syllabus. What about colloids?
Yeah, we have that, sir.
Colloids you have. Okay, fine. Right, cool. So adsorption, we have to understand what exactly it's adsorption, right? So adsorption we know is going to be a physical, a surface phenomena, right? Absorption is going to be a bulk phenomena, right? Your teacher would have told you so many examples of adsorption. Say a chalk dipped in an ink bottle or a water bottle. You will see that the water particles or the ink particles will only be on the surface. And if you're going to break the chalk and see, you are not going to see any ink particles or water particles inside the bulk of the chalk, right? So absorption happening only on the surface is what is called as your adsorption, right? And we can easily understand why this happens. Any logical explanation, if I have to give you, it's pretty easy to understand. So now assume that this is the solid, right? So if I take any solid in the bulk, sorry, any particle or any atom in the bulk, right? So you see, I'm going to have so many atoms, obviously, like this, right? So all the attractive and repulsive forces are going to balance each other for a particle which is inside the bulk, because all side I have other particles and atoms, right? Now, when I go to the surface and I take a particle, right? Say down, I have this side, I have this side, I have, but at top, I don't have anything, right? So what I understand is for all the particles which are there in the surface, there will be a net residual downward force. Okay, because there's nothing at the top. So the net force will be acting downwards. Okay, right? So because of this net residual force, if something is going to come, right, it is going to get adsorbed onto the surface of this particular substance. Okay, now there are 2 keywords here. One is what is called as adsorbent and adsorbate, right? What is adsorbent? What is adsorbate? Tell me. What is adsorbent and what is an adsorbate? So basically, one is going to be the one which is getting adsorbed, and the other one is the which is providing the surface. That is the other one, which is what?
Provides the surface is absorbent.
Yes, absolutely, right? This is the one which provides the surface, right? This is the one which is getting adsorbed, or not absorbed, adsorbed. This is the one which is getting adsorbed. Okay, very simple. Now I can have two different types of adsorption, right? Two different types of adsorption can be physical adsorption and chemical adsorption. It's all about what is the interaction between the adsorbent and adsorbate, right? If it is going to be a mere van der Waals force, right, it is going to be called as physical adsorption. Now, if it is going to be an actual chemical bond which connects your adsorbent and adsorbate, then it is going to be called as chemical adsorption or chemisorption, right? And in your NCERT, they would have given you a table, very, very important, right? Say there are a lot of differences. Obviously, all adsorption processes are exothermic in nature, because you see some kind of bond formation is happening, some kind of attractive forces are dominating, is it not? Whenever you have attractive forces dominating, energy will be released. I don't know whether you already discussed. For breaking a bond, we have to supply energy. Whenever a bond is formed, it is going to release energy. Okay, so some kind of bond formation happens here. So all adsorption, whether it's physical adsorption or chemical adsorption, it is always going to be exothermic in nature. So exothermic means delta H is always going to be, delta H will be negative or positive?
Negative.
Negative. Good. Right? For an exothermic process, delta H is negative. Okay. So for all adsorption processes, delta H will be negative. Okay. So how much is the negative value? For physical adsorption, it is not that strong of an interaction. So the amount of adsorption, I think it will be around some 20, minus 20 to minus 100. I'm not sure about the numbers. So it's minus 20 to minus 100 joules. I think it will be for, this is for physical adsorption, and for chemical adsorption, it will be, I think, in kilojoules, if I'm not wrong. Okay, please look at the numbers, right? Okay, so what I have to understand is, since in chemical adsorption, the interaction is stronger, more and more is the strength of interaction, more and more will be the energy released. Okay, and physical adsorption, I'm going to have lesser amount of energy released. Okay, right. And for the same reason that in physical adsorption, it's only a mere van der Waals force, it is reversible in the sense that the opposite process, that is desorption, right, can happen very easily here. Adsorption, the opposite process is desorption, right? So since the forces are little very small, I'll be able to again do the opposite. I'll be able to remove the adsorbent and adsorbate. So that is going to be reversible. That is why we call physical adsorption as reversible. And your chemical adsorption, since it is strong actual chemical bonds, it is going to be an irreversible process. Right? Fine. And temperature, right? Temperature, how it affects adsorption, you have to understand, right? So since all these processes are exothermic in nature, right? Since all these processes are exothermic in nature, generally speaking, if I increase temperature, the extent of adsorption decreases, because it's an exothermic process. For an exothermic process, already heat is coming out. If you supply heat, it is like doing the opposite process, isn't it? So generally speaking, if you increase the temperature, the extent of adsorption decreases. Okay, now this holds perfectly good for physical adsorption, but there will be small changes in this, whatever I told you, with respect to chemical adsorption, in the sense that when I initially increase the temperature, the extent of chemical adsorption is also going to increase, right? And after a point of time, still if you're going to increase the temperature, the extent of adsorption decreases. Can you come up with a reason for this? Again, I'll repeat. Initially, if I increase temperature to some extent, the extent of adsorption also increases. But what I expect, it should decrease. But after a point of time, if you're going to increase it, then the extent of adsorption decreases. Can you come up with an explanation for this? Why is it happening like this? The clue is chemical kinetics. did you have Arrhenius equation on all, or that portion is omitted from chemical kinetics? Arrhenius equation, did you have? Is the portion omitted from chemical kinetics, or is it there? Yes, there or not? You don't know that it is there, or not also, or you don't know what is Arrhenius equation. That's why you're blinking like this. Do you know there's something called as activation energy? Have you ever heard this term? Have you heard? Yes or no? Did you hear this term activation energy? Have you ever
Yes,
heard this term? Okay, good. So that means you have Arrhenius equation. If you're wondering what is Arrhenius equation, K is equal to A e power minus EA by RT. Did you see this equation? Is it there in your syllabus?
It's deleted, sir.
Wonderful. Great. All good things only they'll omit. Fine. So that is why I understand why you're not able to answer. So please understand, people. For any chemical reaction to happen, right? For any chemical reaction to happen, right? The reactants initially will have some energy, right? And that energy is not sufficient. Any reaction for that matter. Any reaction for that matter. That energy of the reactant is not sufficient. So the energy of the reactant has to little increase. Okay, and this increase in energy, the reactant's composition will also change. Okay, if I have to show it in some of your graphs, fine. Okay, we'll look into it. Right. So if I plot a graph between potential energy and reaction coordinates. Reaction coordinate means reactant to product. Whether it's a reactant or it's something else, or it is the product, intermediate and the product. Okay, fine. So this will be the initial energy of the reactant. Initially, this will be the energy of the reactant. Okay, right. Now, collision theory. Did you study? Collision theory is also omitted from chemical kinetics. Okay, I think from not getting answers from you, so I can understand that it is omitted. Okay, so what you have to understand is, people, right? So you have reactant molecules. Say I have A and B are the reactants. Okay, now this A and B has to undergo collision. This is what collision theory says. For any chemical reaction to happen, for any reactant molecules to react, right? They must undergo collision with each other. Okay, now when they collide, they are going to form something like this. Right, and this is what is called as your or I would say the transition state, TS. TS is what is called as the transition state, and this transition state will eventually form the product. Okay, this transition state will eventually form the product. Okay, right. So this collisions will happen, but for this collision to be successful, in the sense that this collision forming transition state and to form the product, that is what is a successful collision. Okay, so for it to have a successful collision, right, there are two criteria. One criteria is there should be enough energy possessed by these two atoms so that they will be able to form the product. The energy of the collision should be above certain value, just like you have, I don't know whether you studied threshold frequency in photoelectric effect, right? After a minimum frequency, only if you provide a frequency beyond that frequency only, then photoelectric effect will happen. Right? Similar way, only if the energy is beyond certain value, then only it can go into the products. Okay, the other one is orientation. Don't worry about it. Right? So what you have to understand here is there should be some amount of energy, minimum energy possessed by these atoms or by these reactants, so that they'll be able to go into the products. Okay, so what happens is the collision happens, say one time happens, second time happens, third time maybe they'll have enough energy and then they'll go into the products. Right, so as the more and more collision happens, the energy keeps on increasing. Okay, so you see that initially the reactant energy is very less. Now collision will keep on happening. So now they will reach the enough energy. Okay, I have reached enough energy. Okay, now this enough energy the thing which is formed here is what is called as your activated complex. Right? This what you have here is what is called as your activated complex, the transition state which I'm talking about here. Okay, right. Now the energy possessed by the activated complex, this difference in it, this is the energy of the reactant, this is the energy of the activated complex. This difference in energy is what is called as EA. EA is activation energy. To activate the reactant. Activate the reactant means to convert the reactant into the activated complex. Right? The energy required is what is called as your activation energy. Okay, right? So now then eventually the product formation starts. Now there will be decrease in energy, and eventually you see that this is where I have the product, this is where I have the reactant. Okay, so this is what is called as your energy profile diagram, which should have been thought is very, 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 very important for us to understand the mechanisms of reactions. Okay, right. So this is what I'm talking about, the energy of activation, the activation energy, right? So when chemisorption happens, initially the adsorbent and adsorbate are not activated, right? So when you supply little amount of temperature, that is actually going to satisfy the energy gap, the EA, right? Now, so that's what I told. Till a particular temperature, if you're going to supply energy, there will be increase in adsorption because the activation energy is getting satisfied, right? But after a point of time, then the normal thing happens. Now the bond formation starts. Still, if you're going to supply energy, you see that there is decrease in energy happening. If you're going to supply energy, the opposite process will happen, right? That is why you see until a point of time, temperature increases, extent of adsorption increases, but after that particular point, you see that increase in temperature will decrease the extent of adsorption. Okay, right? So see, if they ask you this question, why is there a change like this? Just give the word of activation energy. Okay, just to explain them what is activation energy. Well, you don't have to explain what is activation. If you just give the term activation energy, that would be sufficient. Okay, fine. So that is about physical adsorption and chemical adsorption. Even though it is not there in the syllabus, for understanding the basic concepts of chemistry, you have to know all this. Okay, that's why I spent some time on with this. Okay, right. So that is about physical adsorption and chemical adsorption. And then what you have to look into is adsorption isotherm. Freundlich. Oh God, I forgot the spelling. Okay, got it. Freundlich isotherm. Freundlich adsorption isotherm. Right? What do you mean by isotherm? Isotherm is a graph which is obtained at constant temperature. Between any two physical quantities, pressure versus volume, you draw, but you keep temperature constant. That becomes an isotherm. Okay, so here what I'm going to see is the graph between. Okay, fine. We'll not look into like this. We'll just see what it says. So what it says is the extent of adsorption. Right? The extent of adsorption is directly proportional to the pressure supplied. Is it not? Now it's pretty easy for us to understand. Say, assume that I have a surface, right? I have gaseous molecules coming. Okay. Now, if I increase the pressure from the top, or the pressure which I supply, or the pressure of the gas, whatever it is, right? If the pressure of the gas or the pressure you supply, if you're going to increase the pressure, it's pretty understood that you are going to make close contact with the surface and the gaseous molecule, right? So obviously more and more contact, more and more will be the extent of adsorption, right? That is what is given by the statement. The extent of adsorption is directly proportional to the pressure. Either the pressure of the gas, if you're talking about a gaseous adsorbate, right? Or if you're talking about some solid and liquid, then if you increase the pressure, then also the extent of adsorption is increasing as you increase the pressure. Okay, now this extent of adsorption, how do we see it mathematically? The extent of adsorption we can see mathematically by this term x by m, right? Where x is the mass of adsorbate and m is the mass of adsorbent. Okay, right? X is the mass of adsorbate and m is the mass of the adsorbent. But that means for a particular surface, if I have some mass of the surface, to that particular mass of the surface, how much adsorption can happen of a particular thing just coming to the surface. Okay, so that x, so how we can write this equation now? X by m will be some directly proportional. We should not say p, it's actually p to the power 1 by n. That's what we should tell, right? So it's some exponential, that's what you understand. Okay, so x by m, now if I remove the proportionality sign, it will become k p power 1 by n is what I have. Okay, right. So, right, if you look at the graph, you will see, if I put x by m versus pressure, right? So at very low pressure, when the pressure is pretty less, right? Initially only I'll have. So when the pressure is little less, you will see that I'm going to have a straight line. Okay. Now at very high pressure, you will see that there is going to be an exponential increase. At very high, if I have to show it, I'm not showing it properly maybe. So this one, say an exponential increase, and then after a point of time, there's nothing going to happen. After a point of time, saturation is going to happen. Okay, because obviously all the points would have been occupied. There is no more point, there is no more place for something to come and get adsorbed. That's why you see, even though increase in pressure, the extent of adsorption is not changing. Okay, right? So until this point where you see a linear increase, I can write the equation like this: x by m is equal to k p. Yeah, k into p. Okay, right. Now at this particular curve, which you see exponential increasing, this term holds good. Kp power 1 by n, exponential, right? And at this point, if you're going to see, I have x by m is equal to k, p power 0. It's understood. The pressure is not going to have any particular effect on increasing the adsorption, right? So x by m basically will be equal to k. That's why you see a straight line parallel to x-axis. Okay, right. Now same thing can be done with the help of logarithm on both sides. So if I take log on both sides, it will become log of x by m is equal to log k plus 1 by n log p. Hope you understand how this equation came. Just taking log on both sides. Log of ab will become log a plus log b, and log of a power b will become b log a. All things I did here, right? So if I'm going to plot a graph between log of x by m versus log p, now you can see that log x by m is what is y, right? And log p is what is x, right? So this is like what? Y is equal to mx plus c, where m is 1 by n, mx, 1 by n is m, and this c is what is my log x. So positive slope. You will get a straight line like this. So please bear with my marker, I'll buy a new one, don't worry, right? Okay, so this is what is the straight line you will obtain, and this point, the intercept, is what is my log k, and the slope of this line will become 1 by n. 1 by n is here. That n depends on what is the adsorbent, what is the absorbent. It is substance dependent. Okay, right? So that is about your adsorption. What is the time? Okay, so we have just your colloids, right? Maybe that we'll see tomorrow. Okay, right? I'll just take 10 more minutes is what is required for us to finish colloids. Nothing much. There's nothing to teach. It's pure theory. Or what you do is you study it and come tomorrow. You study the entire colloids, right? And then if you ask me questions, that will be better. Whatever questions you will ask, that questions alone I'll answer, and then move on to the next chapters. Can we do that tomorrow? Will you do that and come? Everybody will do that and come. Colloids. Will you study and come and ask me your doubts? Will you do that? Okay, cool. Right? Rather than me telling you whatever you know, I don't know what you know and what you don't know. That's the point. Right? So you study it and come. If you have any questions, you ask me. If nobody has no questions, then we'll directly move on to the next chapter, whatever is given in this. Whatever is given in the schedule. Okay. I hope you learned something today. Right? Fine, guys. Thank you so much. We'll meet again tomorrow. We have a class. We'll meet again. Thank you so much. Bye bye. I'm closing it.
Thank you,
Thank
sir.
you, sir.
Thank you. Thank you.